A century and a half ago, the deep ocean was viewed as a global desert. Scientists assumed the seafloor was a predictable, featureless expanse of mud and silt, a vast, frozen world where the processes essential to life simply came to a standstill. In 1875, the crew of the British ship HMS Challenger was nearing the end of a 4-year mission to map that presumed plain. 2,000 kilometers east of the Philippines, they performed a routine sounding. But the lead weight didn't touch the bottom at 3 kilometers down, or 5. The rope kept sinking past 8 kilometers, pulling into a void right underneath the ship's thin wooden hull. They had found the Mariana Trench. Had they been slightly further west, they would have hit the Challenger deep. If you dropped Mount Everest into this hole, the entire mountain would disappear, with 2 kilometers of water still sitting above its peak. That single accidental sounding proved the ocean floor wasn't a flat desert.
It was a landscape of extremes, hiding unmapped chasms holding the deepest secrets on our planet. This chasm is the result of a massive geological conveyor belt. The Pacific Plate, a slab of ocean crust 170 million years old, moves steadily westward across the globe, driven by thermal currents in the magma below. When this dense, cooling rock hits the younger Philippines Plate, gravity pulls it down. The Pacific floor bends, sinking under the continent and returning to the magma from which it formed. This process, called subduction, is the largest recycling operation on the planet. The trench is a zone of active destruction, where rock faces kilometers deep grind together. It is an environment of unimaginable mechanical force, raising the question of how anything biological could exist within such violence. Our journey into that void begins at the surface. In the epipelagic zone, sunlight powers photosynthesis, splitting carbon dioxide to build every life form we are familiar with. This is the sunlit layer that supports the tuna, whales, and sharks we recognize. Plunge past 200 meters, and the light fades into the twilight and midnight zones. Without the sun, predators rely on bioluminescence to hunt, or use sensitive pressure sensors to detect movement in the pitch black. In a world where food is scarce, many species have adapted through deep-sea gigantism. A larger body allows an organism to go longer between meals and eat larger prey when it finally arrives. The giant squid is the most famous example of this scale. Reaching lengths of 13 meters, these monsters use the largest eyes on Earth to scavenge in near-total darkness. Stripping away sunlight removes the standard rules of survival, forcing life to mutate into predatory forms specialized for the dark. At 6,000 meters, we enter the hadal zone. The temperature is near freezing, and the water pressure becomes 1,000 times greater than at the surface. It's the equivalent of a 1-ton weight resting on your thumbnail, enough to destroy most cells. This force is unforgiving even to our strongest machines. In 2014, the unmanned exploration vehicle Nereus suffered a catastrophic implosion during a dive into a Pacific trench, its reinforced hull instantly crushed by the weight of the water. Humanity first braved this pressure in 1960. Explorers Don Walsh and Jacques Piccard descended in the Trieste, a steel pressure sphere. At 9 kilometers down, a plexiglass window block cracked under the strain, but they continued for another 2 kilometers until they reached the bottom. If the weight of this water can buckle metal and shatter plexiglass, the fact that we find soft, organic life at the bottom suggests a biology that operates on a different set of physical principles. On the floor, 11 kilometers down, we find amphipods and sea panks scavenging for organic particles. They thrive in an environment that should, by all accounts, completely bring the processes essential to life to a standstill. Most surprising are the xenopyophores. These single-celled organisms grow to the size of a football. It is a scale that seems impossible for a single cell, thriving in the same pressure that implodes our armored submersibles. This ecosystem is powered by the Earth itself. Deep fissures vent columns of mineral-rich water, allowing microbes to perform chemosynthesis, extracting energy from chemical reactions rather than the sun. This creates a self-sustaining world. Microbes feed on volcanic chemicals, and in turn become the food source for everything else in the dark, forming a cycle of life entirely detached from the surface. Re-emerging to the surface reveals the true gap in our knowledge. While we have seen glimpses of these alien ecosystems, the vast majority of the deep ocean remains a mystery. Exploration is rare because the technical challenges are so high. The number of people who have visited the Challenger Deep only recently exceeded the number of people who have traveled to the moon. This chart shows how little we've cataloged. Scientists have identified only 400 species in the global hadal zone. In comparison, a typical freshwater lake often supports thousands. Most of our data comes from dropping a camera into the same small spots. We are trying to understand a trench system that spans an area larger than Australia by looking through a single viewing port in the dark. Studying how these organisms adapt their cellular chemistry to withstand such pressure gives us a rare window into how life can be re-engineered. These biological oddities are where we find the chemical blueprints for new medicines and the secrets of how life first began in the dark. We have only just started to light up the abyss.